All right, statisticians, today we will be talking about probability, specifically the ideas of randomness and how probability and simulations can help you answer various examples. Let's go ahead and look at some vocabulary. First off, we have a random process, which is something that generates outcomes that are determined purely by chance. For example, rolling a six-sided die is a random process, and a trial is just one repetition of that random process. So if we were to roll a six-sided die, that would be considered something random. And then a trial is the fact, or the trials is the fact that we are rolling that die 10 times. Now, directly below, we have another example of a random process, flipping a two-sided coin. What we have here on the left is the result of flipping a two-sided coin, looking for heads, and doing that only 10 times. Whereas on the right, we have that exact same coin now being flipped 50 times. Let's look at some definitions right down here, starting with probability. The probability of any outcome in a chance process is some number between 0 and 1. And when we say something between 0 and 1, we mean like 0.5, which represents 50%, or 0.33, which represents 33%. Those are the numbers between 0 and 1 that represent probability. And that probability is going to describe the proportion of times the outcome would occur when that is happening over a very long series of repetitions. And that is where the law of large numbers is going to come into play. The law of large numbers says that if we observe a bunch of repetitions of any chance process over a large amount of time, that result is going to approach its true probability. So as we can see, when our repetitions hit around 500 times of flipping the same coin, you are consistently getting a result that is hanging out around the 0.5 range, or the 50% marker, which makes sense. There's only two sides of a coin, and you have an equal chance of getting heads or tails. But when you only flip that coin, let's say 10 times, you're not going to see a consistent, repetitive result of getting 0.5. It's going to be bouncing around a little bit more, but again, the law of large numbers, when you are doing the same random process a long enough period of time, the true probability of the result is going to be revealed. Let's take a look at an example. Holy cow. The Chicago Cubs play their home games at Wrigley Field, located in Lakeview neighborhood of Chicago. A recent New York Times study concluded that the probability that a random selected Lakeview resident is a Cubs fan, that probability is 0.44. Now, part A. Interpret this probability as a long-run relative frequency. So long run means over a long period of time. If we randomly select a very large sample of Lakeview neighborhood residents, we would expect about 44% of them to be Cubs fans. That is the meaning of 0.44. 44% of the neighborhood is a fan of the Chicago Cubs. If a researcher randomly selects 100 Lakeview residents, will exactly 44 of them be Cubs fans? Let me actually just back up some of this ink that I wrote a little earlier. There we go. Will exactly 44 of them be Cubs fans? Explain your answer. And no, definitely not. A probability is not going to be exact when it is a small group of people. There are way more than 100 residents in the Lakeview neighborhood area around Chicago. So if you only look at 100 of what is a very small amount of the total residents, you would not expect exactly 44 of them to be actual fans. It would be surprising if you got that answer, but at the same time, you're not asking enough of the residents if they are fans or not. So no, a probability is not going to be exact when the sample size is relatively small. Here's another few definitions right here. We have a simulation, and that is the imitation of chance behavior. And it's usually based on a model that accurately reflects the situation. That model could be generated from a computer. It could be something you are doing by hand, again, rolling a pair of dice, flipping a coin. And the process for describing a simulation is as follows. When you are responding to a question that asks you to explain a simulation, you want to start by describing how you are using your chance device. Are you rolling some dice? Are you flipping a coin? Are you using computer software to randomly generate a number? And that is simply explaining what one trial of your simulation is going to be. Then state what you are going to look for. Are you looking for a result of heads if you are flipping a coin? Are you looking to roll the number 6 if you are rolling a die? Or if you're picking numbers between 1 and 365, are you looking for numbers to repeat? You just have to state what it is you are doing with your random process. Then perform many trials. Describe the repetition process of using that chance device, and then the results you get can be used to answer whatever the question is that you're looking for. Again, if you were, let's say, flipping a coin, maybe you're you're looking to see how many times you get heads 3 times in a row over 50 flips. And then your simulation would be flipping the coin 50 times and documenting every time you got 3 heads in a row. But you would use computer software to do all of this for you. That is the point of having a simulation. Or if you're doing something over a large enough period of time, you wouldn't physically do it yourself. You would use software. So let's look at a very famous problem called the birthday problem. In a certain AP statistics class of 24 students, 2 of the students discovered that they share the same birthday. Surprised by these results, the students decide to perform a simulation to estimate the probability that a class of 24 students has at least 2 students with the same birthday. Just to reiterate what's going on here, we have a class of 24 students. 2 of them have the same birthday. The students in the class are thinking to themselves, wow, that seems odd. There are 365 days in the year, and 2 of us had the same birthday. Well, we can run a simulation to see just how likely it is that any 2 students, or at least 2 students, share the same birthday. I mean, who knows? Maybe 3 or 4 of the students all share the same birthday. So in order to do this, we are going to assume that birthdays are randomly distributed throughout the year, and we are ignoring leap years. Let's describe how to use a random number generator to produce this situation. And here's what you can do. These 4 things are the ingredients that go into describing how you would use a random number generator. So listen carefully. It's easy, but you need to be descriptive from a statistical standpoint. You start by labeling each day of the year by the numbers 1 through 365. Just order them. January 1st is the number 1, and then December 31st would be the number 365. Describe your assignment of values to whatever it is you're looking for. Then use your random number generator to generate 24 random numbers from 1 to 365. State what the random process is going to be doing. We started by describing the numbers 1 through 365 that they're going to be labeled, and then we stated how a random number generator is going to spit out 24 of them at a time. And then what are we looking for? What is the goal of repeating this again and again and again? Well, we are looking for any 2 students that share the same birthday. And then lastly, you want to talk about your results. And the results would be counting the number of times that 2 or more students shared the same birthday. Now, I did not write out 24 numbers, but the basic idea is as you are using the random number generator, it's going to give you one number at a time. Let's just say it gives you 100, and then 24, and then the number 1, and then the number 6, and then another number 1. And there you go. Without even going all the way to 24 numbers, you got 2 numbers repeating, which would mean that in a group of 24 students, 2 of them have now just had the same birthday. But then again, I'm just making up these numbers on the spot, and I am not a random number generator. Let's dig a little deeper into this situation. The dot plot that you see off to the side is showing the number of students who share a birthday with another student in the class of 24. And this dot plot is representing 50 trials of this simulation. 50 times a random number generator produced 24 numbers. And as we can see in many of those trials, none of the numbers were the same. 0 of the students shared a birthday in that many of the trials. But we can also see that there are students who did share a birthday. So, part B. Explain what the dot at the number 5 represents in the context of the problem. Well, that number 5 means in one trial, there were 5 students who share a birthday. For example, maybe all 5 of the students had the same birthday. So maybe the random number generator spit out the number 1 5 times out of all of the 24 trials. And that would correspond to January 1st. And that is one interpretation of that single dot. But another interpretation would be out of the 5 people, 2 of them shared one birthday, and then the other 3 people shared another different birthday. And that would still fulfill the requirements of at least 2 people sharing the same birthday. So hopefully that makes sense. Please drop a comment if that part of the explanation does not make sense, so I can try to clarify that in the comments. Let's just look at part C. Use the results of the simulation to estimate the probability that a class of 24 students has at least 2 of them with the same birthday. And then were these results surprising or unusual in any way? So, listen carefully. We can observe that there were 26 dots that were not on the number 0. That means 26 of the students there were 26 students that shared a birthday with at least one other student in the course of all of these trials. That's what it's saying. So in individual trials, it would not be 26 students that all shared the same birthday. It's just that out of all 50 trials, it happened 26 times that 2 students shared the same birthday. So once again, this 26 does not mean that in one instance, 26 students had the same birthday. The class was only filled with 24 students. This output means that out of 50 trials, 26 times, two of the students actually had the same birthday, or at least two of them did. In multiple trials, it was more than two of them that shared the birthday. So 26 out of 50 times, there were at least two students who had the same birthday. That is a very large probability. It would not be surprising, therefore, that in a class of 24 students, you would get two of them having the same birthday. It is just random chance. It just so happens that out of the 365 days in a year, the likelihood of two students having the same birthday in one class is over 50%. And for things to be statistically significant, for things to be surprising and unique, we need those things to be at or below 5%. That's just kind of the threshold. And since this event happened more than 5% of the time, in fact, we had a success 52% of the time, then that means it is due to random chance that two birthdays could be the same in a group of 24 people. Hopefully that makes sense. If not, well, that's why we have some other examples. And again, drop a comment. Let me know if something in that question just needs to be clarified a little bit more. Another example problem. Names in a hat. Suppose I want to choose a simple random sample size of 6 from a group of 60 seniors and 30 juniors. We want to be sure that 4 of the people you pick are seniors and 2 of them are juniors. In order to do this, we are going to write everyone's name on a piece of paper that are equally sized, and we're going to put them in a bag or a hat. We're going to mix them up, and then we will be selecting the names one at a time until 4 of them are seniors and 2 of them are juniors. So it doesn't matter what order that happens in. We just need 4 seniors and 2 juniors as we are drawing names out of a hat. It takes 14, in this situation, which is made up, it takes 14 name selections in order to get 4 seniors and 2 juniors. 14 names had to get pulled out of the hat in order to do that. Does this outcome provide convincing evidence that the names were not properly shuffled? We might think that we should have gotten a successful result of getting 4 seniors and 2 juniors with less than 14 names being drawn. So we are trying to see if there is evidence to suggest that the shuffling wasn't done well enough. To help answer this question, we want to perform a simulation to estimate the probability that it will take 14 or more selections to get 4 seniors and 2 juniors. We just want to model this scenario and see if after using a simulation, it makes sense that it would take 14 trials. So once again, describe how to use Table D to perform one trial of a simulation. Table D is basically a set of random numbers, and you can find the lists for Table D on the internet anywhere. It basically will give you multiple lines of random numbers, and you will choose one of those lines and do the following procedure of choosing random numbers, which is talked about in a previous video on collecting data, so I will assume you're familiar with this process. To describe a random process, a simulation, you want to start by describing how you will be labeling your numbers. So in this case, we want to get 60 seniors and 30 juniors. So that means we need 2-digit numbers. We are going to assign the first 60 numbers that we are putting into a hat, seniors. So 01 all the way to 60 will represent the seniors. And then the numbers 61 through 90 will represent the additional 30 juniors whose names are going to be put into the hat. And then the numbers that are beyond 90 are numbers that we would ignore. And any numbers that repeat, we also will ignore. We want 4 unique senior numbers and 2 unique junior numbers. Next, once we have our names put in a hat, we are going to, or not put in a hat, we're using Table D. Once we have established the labeling of the seniors 01 all the way to 60, and then the juniors 61 to 90, we are going to use repetition to repeatedly choose 2 numbers at a time from our Table D, and we're going to write them down. And then we are going to observe how many of those numbers are the same. We are going to state, based on looking at all of the results, how many numbers had to get picked. And that is where we simply tie in the results that we were looking for. We wanted 4 seniors and 2 juniors. So here's what that's going to look like. We're going to perform 2 trials of the simulation using the random digits below, and then we're going to clarify the procedure that basically happened here. We have one line from Table D. I'm not sure which line this was, but it's just what was presented in this example. So we are going to start by taking our first trial, and we're going to group numbers 2 at a time. So you can see where the numbers 15, 18, and 53 all come from, that first part of Table D. We are crossing out 95 because 95 is bigger than the maximum number in our situation. And then right here, once the number 19 hits, well, all of the numbers that are from 1 to 60 represent seniors. So we are now done with getting our seniors. We need 2 numbers that fit within in the junior range of 61 to 90. So as we continue going from left to right using table D, we can see that the number 12 comes up next, followed by 83. 83 would be a number corresponding to a junior, but we needed two numbers that corresponded to a junior. So we have to keep going. And in choosing multiple more numbers, we have arrived at the number 51, which was already repeated earlier, so we can exclude it. Then you get 97 outside of the range, but then it happens, 87, which is a number representing one of the juniors, and we have now completed this trial. It took us 10 unique numerical selections in order to get 4 seniors and 2 juniors. We are looking for 14 students. That's the number that actually happened. And now we are just replicating this procedure. In the second trial of doing the same thing, just pick up where you left off on table D. You don't start over. You don't have to go to a different line. Just continue where you left off. So starting with that 61, we immediately get 61, 10, and 90, with 61 and 90 being in the range of juniors. So we are now done choosing juniors, and now we have to choose the rest of the seniors. So that is where we simply continue, and then the numbers 43, 56, and then 42 pop out. We ignore 64 because we, again, only wanted 2 juniors, but this time it only took us 7 unique numbers in order to meet the goal. So since neither trial showed more than 14 students needing to be picked, it probably suggests that things weren't mixed up well enough. So let's dig a little deeper into this for one more situation. In 50 trials of the simulation, there was one instance for which the number of names actually took 14 selections or more. And do these results suggest that there is convincing evidence that the names were not properly shuffled? So in a simulation that was done with computer software, only 1 out of 50 actually took 14 names or 14 numbers in order to pick 4 seniors and 2 juniors. 1 out of 50 is 2%. That is a very, very small percentage. So yes, that is convincing evidence because less than 5% of the time the result actually happened. The statistically significant result took place. It would be very unlikely to go through 14 names and get a sample of 4 seniors and 2 juniors. It's way more likely that it's going to take you less than 14 selections in order to do that. So since 14 only happened, or 14 name selections, numbers happened only one time, that would suggest the names were not properly shuffled, because that shouldn't happen. We just saw 2 trials where 10 and 7 were the amount of numbers that had to be drawn, and out of 50 trials, it took 14 name pulls. It only happened once where it took 14 name pulls. That's incredibly, incredibly small. So if that actually happened, which is what happened all the way back over here, it takes 14 name selections. That's what truly happened. That is a very, very unique situation, because using 50 trials revealed that it only happened once, then it is statistically significant, and we can conclude that the numbers were not really mixed up that well. Hopefully this gave you at least a mild overview of probability and simulations, and if you have any follow-up questions, please drop a comment. Let me know what point in the video you need some more clarity, and I will do what I can. All right, statisticians, I will see you next time.